recording this. Okay, so the idea today is that we learn how to solve differential equations in the computer, okay, numerically. So what does that mean? It means that you're not going to find a solution itself. So let's see. So this numerical. Please, my handwriting is pretty terrible, okay? But then, if you cannot read, please tell me in the back, especially. Yeah, numerical integration of ordinary differential equations. Okay, so this is what we're going to talk about today. Yeah. So. So you have seen a lot of ODEs by now, right? So we are now studying systems of two coupled ODEs, okay? But you have seen a lot of this right now, right? So equations like this, where you have the derivative of x, right? So x is a function of t, of time, okay? And then you have that the derivative of x is some function of x and t, okay? So for instance, you have seen the exponential growth equation that is like this. You have seen logistic equation. I don't know, have you seen any other equations? Or I don't know if Roberto showed you some equation that is not that is also dependent on time. Have you seen something like that? Only autonomous. Yeah? No autonomous. So what is he talking about? When you have an equation, an ordinary differential equation, where t doesn't appear explicitly here in the right-hand side, okay? Of course, depends on time because x depends on time, okay? But here it doesn't show explicitly. Okay? Of course, you could have something that changes explicitly on time. For instance, if I have a population that has seasons, okay? So there's a seasonal there's a growing season, for instance, so that, for instance, either the growth rate or the carrying capacity change over time. So it would be something like, okay, if it were the carrying capacity, I could, instead of writing this, where k is a constant, I could write something like this. The t is Rx 1 minus x over something like, I don't know, k plus alpha sine of t, okay, something like this, right? So this means that the carrying capacity grows and decreases over time, okay? It has a periodic shape. This would be possible, okay? So this would be a non-autonomous equation that means that it depends explicitly on time, okay? So in general, the general form of this is that this function f can depend both on x and on time, okay? Okay, so far so good, okay? So nothing new here, okay? So what I want to do here is, okay, many equations, right? So these two equations here, you have seen the solution, the general solution of these equations explicitly, right? So we can come here and tell you, okay, if I give you an initial condition, okay, given an initial condition, so given initial condition, what is it? This x at time 0 equals some constant at 0, okay? I can take, for instance, the first one here, okay? And I can write down x of t equals at 0 times exponential of rt, right? So I won't go into this because I think Roberto already talked about this quite a lot, okay? But then you see, for any value of r and any value of the initial condition, I come here and I tell you what the solution is for all times, okay? So this is what we call an analytic solution, okay? This is usually impossible to find, okay? For most equations in real life, you cannot find this kind of analytical solution, okay? You can't. So you can also find this for this equation here, but for most equations that you'll find, that you're studying in real life, and even for the rest of Roberto's course, okay, because he was just starting for the equations that he's studying now with systems of two equations and other stuff, you cannot do this. You cannot find an analytical solution. There's no analytical solution, okay? So how do you study these equations then, right? So there are some techniques that Roberto is going to talk about, that is analysis of fixed points, stability of fixed points, but this gives you an idea of the general behavior of the solution for large time. What if you actually want to know the trajectory over time of the solution? So I have something like, I have an equation like this, and if I don't know, this thing here, how do I find what is the trajectory itself, okay, of the solution, okay? How do I do this? So this is the problem that numerical integration solves, okay? Yeah, so given an initial condition and your differential equation, numerical integration is going to do this even if I have no analytical solution. So this is called a numerical solution, okay? So, so far so good, people. So if you have questions, please raise your hands, okay? Yeah? So, so how do you do this? Okay, so let's step into this, okay? So the idea is, okay, you have this, right? You have this. So you more or less, what do you see? Everyone is comfortable with a derivative, right? Or not so much? Well, it's kind of, it's when you see in a graph over here, right? So what does this derivative means geometrically, right? Or graphically? It means that at each point here, so I have this x as a function of t, at each point here, if I look at this point and look at the derivative, what is the derivative? It's the angular coefficient here of the tangent line over there, okay? Yeah, tangent straight line here, okay? And this here, at each point along this curve, the value of this, the tangent of this straight line here, that is the derivative of this curve at this point here, okay? It will be exactly given by the function f at this point t and x. Yeah? Okay, so if I take this t and this x and substitute here, f of x t, this will have the same value as this tangent here, okay? So this is, and this will hold for all of the points, okay? So this is what the differential equation means, okay? So how do you use this, okay? So, so what do we do to numerically integrate something? We go over here, we have t here, we have x here, and I start at 0 again. So for at 0 here, I will have a value here at 0, okay? And what do I have to do to numerically integrate this? I have to estimate, so I will give you small steps in time, okay? And I go from 0 to first step here. I'll give a time step delta t, and I have to estimate how much the x of t will decrease or increase over this small time step, okay? So it will, for instance, if it grows a bit, it goes from this point to this point, okay? So if I wanted to, for instance, in this case here, if I was here and I want to give a step here, I want to estimate how much the function grows over a given time step, okay? So how do you, so what is this amount of growth here? This is similar to the derivative, okay? This is similar to the derivative, but it's a little bit different, right? Because the derivative is instantaneous growth rate, yeah? And this time step here is not instantaneous, right? So this is a time step, okay? So, so it means that when you do that, you have to do some kind of approximation, okay? So if you remember what is the meaning of the derivative, okay? You remember that dx dt was what? It is the limit of delta x over delta t as delta t goes to 0, okay? or another way of doing this is x, or the limit of x of t plus h minus x of t divided by h, right? Where h is, or maybe instead of h, I will put delta t over here also, okay? So this is like this, as delta t goes to 0. Okay, so this is the definition of the derivative, okay? Is the difference between x of t plus h, so this is t plus delta t, the x of t plus delta t, so over here, okay? So it's this difference here, okay? So it's this difference here divided by this difference here, but only in the limit as delta t goes to 0, right? Yeah? So if I do this, what I can do is I can do something very simple here, that is, I forget this limit for a moment, okay? And I treat this, I treat the derivative as if it was not a derivative, but as a finite difference, okay? And then I rewrite this equation here, okay? I will rewrite this equation here, but changing the derivative for the finite difference, okay? So I will write this equation here, instead of writing it like this, I will write it like this. I'll put this in place of the derivative. So I will write x of t plus delta t minus x of t divided by delta t. This will be equal to my function f of xt. Okay, something like this. Okay, and what I can do now, I can multiply this by delta t and put the x of t to the other side. So x of t plus delta t is equal to, so f of x times delta t plus xt, okay? X of t. Like this, okay? So what does this do for us, right? So what does this do? It gives us how to calculate x at a posterior point in time, given that I have x at time t, okay? So if I start at 0, okay, I have x at 0. I substitute x at 0 over here in the function f. To calculate this, I choose a time step. So I can calculate this, I can calculate this, I can calculate this, and with that I calculate x at the next time step. Okay, so let's try to make an example. Okay, so for instance, let's try to solve the logistic equation, for instance. So yeah, will this work? Yeah. Okay. Nice. So let's solve the logistic equation. Okay. So what does this look like for the logistic equation? So let me write down this, right? So this is x of t plus delta t is equal to, I will invert the order a bit here, x of t plus delta t times what? Times the function f that for the logistic equation is what? Is x of t. I will put explicitly the x here to mean that this x here, right? So the x that appears here is x at time t, okay? At t. I forgot the r over there, right? Yeah. There's an r over here. Yeah. So the function f here is it's r times x of t times 1 minus f of t over k, like this, right? Yeah. Okay. And now let's choose some delta t, right? So let's choose some numbers, okay? So I use delta t over, you see that now there's already a bit of a difference here, right? Because when I had an analytic solution, okay, I could do all this stuff with r and at 0 as variables, okay? You'd put anything there, right? So at 0 and r and so on, or any number, okay? But now I want you should calculate numbers here. I cannot keep doing this calculation with any value of r, with any value of delta t. I have to choose specific values, okay? Otherwise, I cannot move forward, okay? So let's choose, for instance, R equals to 1, delta t equals to 1/2, and I put k equal to 10, right? Let's use 10. And I also need an initial condition, okay? Initial condition I put at 0, 1, I don't know, something like this. Okay, or maybe put at 1, okay, that's 1 is okay. So we don't do so many, yeah, 1. Okay, so we have this. So what does this mean, right? So it means that at 0 equals to 1 means that I know x at 0, okay? So using this formula here, what do I use x at 0, that is 1, and I include all of this here. And what will this result in, okay? This will result in x at the time 0 plus half, okay? So I have x at 0, and using this formula here, I will arrive at x at the time half. What do I do then? I repeat this. I calculate x with another half time step. So then at x at 1, and then x at 1/2. Let's try this, okay? So x at 0 plus 0.5, okay, that is of course x at point 0.5, will be x at time 0 plus 0.5 times r, that is 1, times x, that is at 0, that is 1, or let me write like this, times 1 minus x of 0 over k, that is 10, okay? So this, now I can just use the calculator, right? So to do this calculation. So this is 1 over 10 is 0, 1. 1 minus, can we do this by, do you want to use the calculator, or can we do this just in your heads? It's okay? So, so this is 0, 9, this is 1, this is 1, this is half, so half of 0.9 is 0.45. This is 1, so this will result in 1.45, right? So what we arrive at then, so we started with x at time 0 is 1, now x at time half is 1.45, and now to do another step, I now have x at 0.5, I can now calculate x at the point 1, okay? I do another step, so it's 1/2, okay? So x of 1 will be the same thing as here, but now instead of x at time 0, I use x at time 1/2, okay? So this is x of 1/2 plus half times 1, that is r over here, times x 1.5, okay? X at half, 1 minus half divided by 10. So now I have to probably use a calculator, okay? Right, so anyone can calculate this for me or not? Yeah? Can you put it over there? You have your computers in front of you, right? So please, can someone do this calculation for me? Or maybe I should do this over here in the computer. I don't know. So yeah, so I can just use a new notebook here to do this, right? So just it's 1.45 plus 1 times half times 1.45 times 1 minus 1.45 over 10. This is right, yeah? Did I forget something? No, right? It's okay? Yeah? 1.45. Yeah, I think that's right, yeah. And okay, so you see that in the second step here, I'm already, oh, this always takes a long time, right? So, yeah. And just using Python here as a calculator, right? Probably was faster to open an actual calculator here, but I like this better than a calculator because it shows me the whole expression, and the calculator doesn't remember. Yeah, so this is approximately 2.07, okay? So I'll just round here, yeah? So this is 2.07, okay? Okay, and now what can you keep doing now, right? So everyone's okay so far, so what I can do now? I can calculate x at 1.5, and then x at 2, and then x at 2.5, and so on and so forth, right? Yeah? I just iterate this, okay? Like what do you see here? It's end of a loop, right? So I go in step size of 1/2, okay? Yeah? And what do I end up with, okay? I end up with something that looks like this. I have t here, x here, okay? I have at 0 here that was 1, okay, at time 0. Then I have at point half here, I will have 1.45, and at time 1 here, I'll have this 2.07, and so on and so forth, right? So I'll have other values here, right? So you see that I don't have the full solution in the sense of having, I don't know, it will be something. I'll have not the full solution, I don't have the solution at all points in time, but I have solution in all points in time that I calculated in step sizes of 1/2. Yeah, question? Do you need the mic? There's another over
there. So this just makes sense if your time interval is small enough, right?
Yeah.
Otherwise, it just doesn't go with the equation at all.
The thing is that you are making an approximation, okay? You are making an approximation. And what do we know in related to this, right? Usually, the smaller the time step, the better the approximation, okay? So it's not that it doesn't make sense to have a smaller step size. It's just that
it's a rough
it's a worse approximation, right? So you get a better approximation using a smaller step size.
So there's no way of saying like this is a good approximation until this time interval. That's my question.
Okay, so this is a very good question, right? This is a very good question. So how do we know? So I'll go back to this in a moment. Okay, but this is a very good question. So how do we know? So this is an approximation, right? This is an approximation. So I did this here, and how do I know if this time step is small enough to be a good approximation, or if this is really close to the real solution, to the exact solution, right? How do we know that? So this is actually a hard question, right? So it's oh, I just broke Roberto's chalk. Yeah, sorry. So okay. So first, well, there's a nice thing here that we can do is that this is numerical, right? So we can just put it in the computer for some equation that we know the solution, like the logistic equation, and compare, okay? And see what happens, and see, because I know the exact solution for the logistic equation, right? We have seen this, right? That expression with the exponentials and so on, right? Yeah, so let's try to do this in the computer, okay? So let's go here to the tutorial. So the first part of the tutorial explains pretty much what I just told you here, okay? So this is the first part here, and here, yeah. I have exactly what I just told you here, okay? I don't remember which values I used here. I used something slightly different. Oh, okay, I used R equal to 1, and K equal to 10, and x0 equal to 0, 1, right? So it's, yeah, it's exactly the same thing, but with x divided by 10, okay? Yeah. So you see that I do exactly this calculation here. So I have, after one time step, I will have 0.145. After two time steps, 0.207, then 2.89, then 0.492, and so on, right? So I calculate at each time step the value of f, that is the derivative of x, and I use this expression here to calculate it in the next time step, okay? So this is a table that I wrote down. I don't think I did this by hand. I think I run the program and copied here. Because, well, if you do 4 times, it's already worth writing code, right? So okay, but let's do the old, because when you do the old, okay, you can do this for any time step, any number of times you want, okay? Yeah? So this is the old for it, right? So this is a nice old that I wrote. This dt here is the delta t. I have a range of values here. I'm going to stop at time 10 over here. So you see that a numerical solution never really goes to infinity, okay? I cannot calculate at infinity. You have to stop after some time, all right? But then you can put this as large a time as you want, right? So if I want, instead of stopping at 10, I want to stop at 100. It's okay, just change 10 for 100 here and you're set, okay? No problem, right? Computing here is literally free because Google is doing the calculations, right? So yeah, in the cloud. Okay, I started this, so I have the range of times here, and I have my logistic function here, where I already included r equals to 1 and k equals to 1 over here. And then what do? I do a loop, right? So I loop over the times, okay? And at each time step, I append what? I append, this is pretty much like our recurrence equation now, right? So what is, when you look at this, right? So this looks like a recurrence equation. The next value is a function of the previous value, okay? So this is, essentially you are transforming a differential equation into a recurrence equation, into a difference equation, okay? So that's why this old really looks pretty much like yesterday's, okay? I have that the new value will be the last value plus dt times the function f calculated at the previous value, okay? All right, so far so good, yeah? Okay, and then I have what? I have that x now. It was a list with only the initial condition, okay? And now it is a list with the whole solution up to 10, okay? Up to 10, excluding 10, of course, yeah? And now I just take this and plot it, okay? I plot the x against time, okay? With dots, right? And now to compare, so these are these dots here in blue, okay? But then I want to compare this with the z solution, okay? So then I take the z solution, so I will use another arrange here. I put this into much smaller time steps because I wanted to draw a line that is smooth, okay? And then I use the expression that you saw. You saw this expression in class, in Roberto's class. Yes, this is exponential of time over 1 plus the exponential of time times the initial condition, and then the air incapacity appears. I think air should appear inside the exponential, but air is 1. And the air incapacity also appears somewhere here, but it's also 1, okay? So it doesn't show up in this expression, okay? And then you see that it's okay, right? It's not terrible, but not perfect either, right? So what can we do to try to see what happens with the approximation and do this exact same thing with larger or smaller time steps, okay? So let's try first, let's make this more terrible, okay? So let's try with dt equals to 1, okay? So what happens is that it becomes quite a bit worse in the middle, right? Yeah? Do you agree or? Yeah, it gets worse, but then if we reduce this, okay? So if we reduce this, now this is in point 1, okay? So this is much closer now, right? Much closer, yeah? And if you see, there's still some visible difference over here, right? Yeah, but it's much better, okay? And if I do even smaller time steps here, okay, oops. It gets even better, you see? Yeah, so you see that it works the way we expect it to work, okay? So as we reduce the time step, this approximation becomes better, and then the solution becomes closer to what is the exact solution, okay? So we see that, that this idea makes sense, it works in practice also, okay? Yeah? Okay. So then we already know that that one way to improve the accuracy, improve the approximation is reducing the step size, okay? But now, but now there's a much harder question, okay? It's a much harder question. That is the following, okay? So this is, I don't even try to over this in the tutorial here. The question now is a different one. So here it was enough easy because I knew the exact solution. So I can tell you pretty confidently that in this situation with this value of R and K and initial condition, if I choose delta T of 0.5, it's not so good. It's okay, but not so good. If I use 0.1, it's okay. And if I use 0.05, then it's pretty good, okay? So I can just look at the plot and tell you this, okay? But what if I have an equation that I don't know the exact solution? What if I don't know the exact solution? I don't have anything to compare. How do I check if I'm using the right step size? How do I know that? Yeah, so this is a problem that in numerical analysis is what we call error control, right? So how do we control the size of the error? Okay, so this is pretty difficult to do in practice. Okay, this is pretty difficult. So the idea is that you have to compare this expression here, right, with the exact derivative. Okay, you can do this. It's kind of there's a bit of you have to work a bit on it, right? So I won't go into this because it requires more math, right? So we essentially take the original, we take s of t, where is it now? Yeah, I just take s of t and I try to expand this into a Taylor approximation and so on, and then I check the difference between the solution calculated using this and the exact solution by estimating the second term in the Taylor approximation and so on in the Taylor expansion. Okay, I'm talking about this. If you don't know what is a Taylor polynomial and so on, don't worry. Okay, just telling for general information. So, but the thing is, there are ways to try to estimate the error. Okay, using mathematical properties of the solution. Okay, so I can try to estimate the error. Okay, and with that, okay, once you estimate the error, what do you do, right? So you do the following. You have to, at each point in time, right? So this is what you're always going to do, right? So this method that I just showed you, this is called, this has a name. This is Euler's method. Okay, so this whole thing that I just did here is called Euler's method. Okay. It's the simplest method for solving differential equations. Okay, but any method is always going to do something like this: calculate it one step at a time. Okay, so the trick here is try to do the following. You do something like this: you do a time step, and then you estimate the error. Okay, and I won't go into detail of how you do this, right? But there are ways to estimate the error. And you say, okay, if this error is larger than some tolerance, what do? I go back and I try to do it again with a smaller step size. And then I check if it still gives me an error that is larger than my tolerance. If it is too large, what do? I decrease the step once again. And I keep taking smaller and smaller steps until I get the right tolerance. Okay, it's still, until I'm inside the right tolerance. Okay, yes? Yeah.
the difference between choosing a really small time step in Norless method and this one that you're talking about right now is that it's going to be more efficient? More optimized.
What I'm describing is not exactly a different method. I'm more describing a technique that more refined methods use, right? So usually, so let's go a bit over, well, those of you from maths and physics and something like that, we usually do a numerical course over your, yeah? Many of you have done that or not? Yeah? So usually you learn more refined methods in the sense that instead of just doing this, right, and do something more, instead of approximating this derivative like this, or using just this expression, you calculate using more points and so on, and do something. There are what is called Taylor methods, there are Runge-Kutta methods, this kind of thing, right? And these are other methods that give you a better approximation for the derivative, okay? So this, what does that mean? It means that with the same step size, with the same delta t, it gives you a better approximation of the derivative, okay? So this is what these methods do. But then these are more efficient in this sense. With the same amount of calculation, you can get better approximations, okay? But this still doesn't solve the problem that she raised, okay? Because even with these methods, you still don't know how small the time step has to be, okay? And any introductory courses on numerical analysis, they never treat this problem, okay? Because it's too hard, yeah? So so even people that have done this numerical analysis course usually don't know how to do that, okay? Because this is pretty advanced, okay? So the idea of more advanced methods that have what we call step control, is that they estimate the error at each time step and then redo the step until they arrive at the desired tolerance, okay? Now, of course, if you, what does this lead to, right? So let me show you a plot here that will enlighten things a bit. So, yeah. So what this usually leads to is that if you have a solution that is like this, so I have something like, my solution will be something like this. So I start here, and I have a, right? Here, if I'm going like, this is more or less, it's almost a straight line, right? So usually if I go in very large steps here, it works more or less okay, right? And then I calculate the derivative here, and I will arrive at something over here, okay? And then if the solution oscillates very fast, I cannot capture fast oscillations with a large time step. So in this region here, I will have to take smaller steps, right? And even smaller when it oscillates more quickly, okay? So here, I have to give even smaller time steps, but then an efficient program will look at this region here and realize that it can increase the time step again because now the function now is smoother, okay? It oscillates more slowly, okay? And now here I can increase the time steps once again, right? So this is what a method that we call that is adaptive time steps, okay? Adaptive time steps, okay? Time steps. Okay, so this is what it does, okay? So this is how we control the size of the error, okay? Yeah?
Yeah, so what would be the advantage of increasing time steps when...
Yes, here I gave you a moderate example, okay? Because here, this time step here is only, I don't know, 5 times larger than this, okay? But sometimes you have something that changes by orders of magnitude, okay? I have some, here I have to go in in steps of 0.0001, and here I can give steps of size 1. I don't know, right? So this is much more computationally efficient to give large time steps than to give small time steps. Okay, if I can give large time steps without losing accuracy, I go faster. It's more computationally efficient to give large time steps. Yeah. If I can do this without losing accuracy. Okay. More questions? So, I won't go into the details of how to do this. Okay. I just want to show you that there is this concept of error control. Okay. And that the thing is, even if you have done numerical analysis, numerical calculus in your undergrad or graduate students, okay, usually you don't cover that, okay. It's very, has anyone studied methods for this already? Yeah, you have. Okay, 1, 2, 3, but with adaptive time step? Yeah? Oh, nice, really nice. So this is very rare for people to actually study this, okay. So even if you have learned your Honji-Uta method, for professional use, for using real life, even Honji-Uta methods are usually not good enough because they don't give you what is the right time step, okay? So this is why what I really recommend people to use is to use scientific libraries, and we will show this here, that already include these techniques, okay? Because it's kind of, it's kind of hard to do this by yourself, okay? Yeah? Okay, so this is what we're going to do next, okay? But now, the one thing that you have to be aware then is that these methods we're going to use SciPy library, these methods, you don't need to worry about the time step, right? So if I were using Euler's method, as we just did, you see that there's a lot of difference between doing time steps of size 1 or 0.1 or 0.05, okay? But these SciPy methods, or these libraries, internally they don't care what you ask of them, right? They are always going to give you precise, pretty accurate solutions, no matter the step size that you ask of them. Okay, so let's try to look at an example of this, okay? So back here. So first, how do we call this? Okay, so there's SciPy here. So let's look at this equation here. So this is essentially the same equation, but now I use different parameters also to show you how to include the parameters into the programming, okay? So I have R equals to 2, K equals to 10, and the initial condition at 0.1, and I import NumPy, and that's what will be here again. And here, what do I need to do in order to solve using SciPy, right? So the first thing, I have to integrate the function inside of SciPy. So SciPy is a very large library, okay? It has a lot of different stuff. A lot of stuff in SciPy I have never even used before, never seen before, so it's really a very large library. And it has several submodules, okay? One of them is called integrate. It's used both for integrating in the sense of integrating a function, but also to integrate, when you solve numerically differential equations, this is also called integrate a differential equation, okay? And we are going to use this function called OGE-int for OGE integrator, okay? So I just import this function. This will be the only function that we are going to use inside this module, so we just import this function, okay? And what do we have to do? So we have to define time steps, right? And these time steps now is really what we want in terms of visualization. You don't need to put a very small time step here just to make sure that the solution is accurate, okay? It doesn't matter for the method. It matters for your visualization, okay? Now the parameters are here and the initial condition. And now what do I have to pass to this OGE-int, okay? We have to pass the function, the right-hand side of the differential equation, okay? we have to pass the initial condition, we have to pass the array of times where I want my solution, okay? And I have to pass a list of parameters that my function receives. So this is the structure of my function f, okay, the right-hand side. It always receives the x, right, the dependent, the variable that I want to solve for, the time, and then a set of parameters. Okay? So any parameters that appear over here, I have to pass them as a list down here later, okay? Yeah, so I could have put already 2 and 10 over here, but if I want to change these values later, it's more useful to write this already as a function of these parameters, okay? Yeah, so that I can, so if I want to change k from 10 to 20, instead of changing my function, when I call the ODE int, I can just put 20 here instead of 10, okay? Yeah, so this makes stuff easier, okay? Okay, and when I run this, what does this do, right? So x now will be an array, so let's stop here. I will print x, okay? So in the middle. So what will x be, okay? X will be an array, you see? With this, the first value is the initial condition that I pass it, that is 0, 1, and successive values will be the values of x at time, which times did I have here? 0.5, 1, 1.5, and so on up to 10, okay? So these are the values of x at these different times, and I now can plot t x against t again, right? Just as we have done over here, okay? So I can put this x over t, I just plot this, and I also plot the exact solution here, right? Just to compare them, okay? And when I do this, let me stop the print here. Yeah, this, like this. So when I plot this, we get a much better approximation. You see that now the dots fall exactly over the exact line, okay? And what if I change the time steps, okay? If I put, for instance, time steps of 1, does this matter? No, right? It gives me less points, okay? So for instance, if I didn't have this last plot here, okay, it would not be, it's not so nice to visualize the solution, right? Because it's too few points perhaps, right? So it's not very nice for visualization, but it doesn't affect the accuracy of the solution, okay? I don't have to worry of choosing a small time step because of accuracy, because the library itself takes care of that internally, okay? I just have to care about, well, if I don't have the exact line, I want to have a more or less smooth solution, okay? Yeah, so that's why maybe I should use a slightly smaller delta t over here, okay? So this is steps of 0.1 here, perhaps, yeah? So this is a lot nicer, right? So if I don't have this, even if I don't have the exact solution, I know the shape of the function pretty well, right? So, yeah. Good, nice, yeah. Okay, so this is the general stuff. Okay, you always are going to use ODE int. You have to remember the order of this stuff here: the function, initial condition, times, and parameters. And your function definition has to follow this order too. This receives x and time and the list of parameters. Okay, and the parameters in a certain order that is the same that they appear down here. Okay, easy. What do you think? Yeah? No, not so much. Perhaps a little bit. Okay. So now that this is okay, so how do I work on a system of ODEs? Okay, so conceptually, it's pretty much the same because so let's so conceptually. So conceptually, it's pretty much the same. So if I have a system of equations, okay, so which ones I can use? For instance, one that you know well already is this one, right? So if I have gx1 dt equals r1 x1 k minus x1 minus alpha x2 over k, and gx2 dt is r2 x2, this is a1, right? So k2 minus x2 minus beta x1, okay, over k2, right? So this is Lotte-Volterra competition, right? And I need an initial condition, so I need x1 of 0 is going to be, yeah, I'll put x0 and y0, right? And x2 of 0 is y0, something like this, okay? So conceptually, so for instance, if you were to apply the Euler method here, it would be pretty much the same, okay? We would have to calculate delta x1 delta t. So I will have x of t plus h minus x of t divided by delta t will be this function here, right? So I will have something like I will have now something like delta or x1 of t plus h will be x1 of t plus delta t plus a function that is this whole function here, okay? What is the difference from the previous is this whole function here, that would be the f function, is now a function not only of x1, but also of x2, okay? So now I will have an f1 here that is a function of x1, x2, and possibly the time, okay? And the same thing for x2, okay? I have something like this, okay? So conceptually, this is exactly, and these are different functions, right? So this function is not the same as this function, yeah? Even though they are very, very similar, they're not the same, right? So conceptually, solving systems of equations, system of differential equations, is exactly the same as solving a single equation, okay? You always do time steps, but now the only difference is that the time step for this function for this variable depends also on the other together, okay? So in order to have x2 at some time t, right, you have to go to calculate both of them together, okay? Because, well, if I start at 0, I do a step as times half for x1. If I want to do this, the next time step for x1, I want to calculate x1 at time 1. I need x2 and x1 at the previous step, at the step half, okay? So I need x2 also at the step half. So I have to do the same steps with both together so that you can calculate this function at the next time steps. Yeah? Is it okay or it's confusing? Yes?
There's something that's kind of strange to me. Solving this differential equation using time steps, we are using discrete time to solve it?
We are. So essentially, there's no continuous in computers, okay? There's nothing continuous, nothing at all. There are no continuous numbers, so this is why I didn't talk much about floating points, but the real line is continuous, but floating points are not continuous. You cannot represent any number with any precision. You have a limited precision. So you cannot really define a continuous function. You only have the function at discrete time steps, okay? So nothing in the computer is continuous actually, right? So yeah, so it's always like this, okay? So back to this. Is it clear the analogy between the one equation to the system of equations? Yeah, so it's conceptually it's exactly the same thing, okay? And all of the considerations that I just told you about apply. You have also to take care of error control and so on, right? To choose the right time step. And now one way to look at this is instead of looking at this as x1 and x2, okay? And it would also have more, right? You would have x1, x2, x3, and so on, right? Instead of looking at this as a set of two equations, right? I will look at this as a set of a single equation for a vector-valued variable. Yeah, so instead of looking at this in this way, well, this is a set of two equations for two variables. I can think of x as being a vector, x1, x2, okay? Something like this. And now this is the vector x at the point t plus h. What is this? Is this vector x1 at t plus h and x2 at t plus h, okay? Yeah? And this will be what? This will be x at t plus delta t times, what is this now? There's f1 and f2, so this is also a vector, right? So this is the vector, that the right-hand side is a function that receives the vector x and returns also a vector with two values, okay? So this will be, I will write it like this, an f of x and t, right? So what is this f thing over here? So this f thing over here is this vector here. So yeah, this f here is just this vector, f1, f2. Yeah, so why is this more practical? Because when we are going to generalize this, it's much easier to think in terms of vectors than to think in terms of some number of equations, you see? Okay, so far? Yeah, does that make sense? So let's look at the computer, how do we make use of this, right? Because now it is even more similar to the previous case, because now I just redefined what was x. X before was a number, and this function f returned a number, right? Now I have x is a vector, and now this f function has to return a vector, okay? A vector with the same number of values as you have in your vector x, okay? So let's end that here. So now if I have two equations, right? So I think I use different equations here. Let's see, a system of ODEs over here. So I use here Lost Volterra predator-prey instead of competition. I think previous courses did it in a different order, okay? But you'll see this in a few more classes, okay? But don't worry about it, okay? So this is predator-prey equation. So V is for victim and P is for predator. So this means the victim here, the prey, increases exponentially in the absence of the predator, but then the predator eats the prey, so it reduces the number of the prey, and the growth rate of the predators is proportional to this grazing rate here, or predation rate here. You see? And if you have predators without any prey, it just dies out. There's this minus GP here that is just a mortality rate, okay? So this is predator-prey equation, okay? And now our variables are V and P. So I have two equations, V, one for V and another for P. But instead of looking at it in this way, we will think about it in terms of a single vector, a single array that is made of V and P, okay? So I import here again, I don't know, just for convenience. So I have a lot of, you see that here I have more parameters. So I have 1, 2, 3, 4 parameters, okay? And I'm going to solve this over time for 50 times that, or up to time 50. I define the parameters here. I have here the initial condition, and now you see the initial condition has to have two values, right? One for V and another for p. Okay, so if I write, and I have to be very careful to always use the same order. Okay, so if I'm going to write that the equation like this, it's natural that v is the first variable and p is the second one. So in the initial condition, the first value is v at 0, and the second value is p at 0. Okay, so always be consistent in the order. Okay, and now I define my function, my right-hand side. Okay, this I called LV. Okay, and it's the same structure as over here. Okay, I have x, t, and the parameters. Okay, and now the same thing. I have x, t, and the parameters. Okay, what is the difference? Is that now x is no longer a number. Okay, it will be a vector, an array. Okay, and the first, so this will have x0 and x1. Okay, x0 is the prey, the v, and x1 will be the predator, right? So I just write exactly those equations here. So in chat here, this is r v minus c vp. Okay, so r v minus c times v times p. This is the first value. You see there's an array here with 2 elements. Okay, I just have a line right here to make it more readable. And in the second line here, in the second value, is the equation for the predator, ECVP minus GP. So ECVP minus G times P, right? Sometimes, if we want to be even more readable, right? If you find this confusing, you can write it like this, and write it like VP is, or V equals to x0, and P equals to x1, and I can just, x1, okay? And I can, instead of doing this, I can write it like this, right? So I can return an array with 2 values that are r times p minus c times v times p, and the second value will be e times c times v times p minus g times p, okay? So perhaps depends on each one, right? So sometimes if you can read this pretty easily, you can write it like this. But if you think it's less error prone, and also do this, right? So that you can use the letters that are easier to read, right? So it doesn't matter, okay? So far so good, yeah? So you see that all of the parameters that I used inside here are here, okay? There's nothing from outside, so all parameters appear in the list of parameters here, okay? And now what do? I just LOG into the end with the name of the function that is the right-hand side. I called here LV for its logical Volterra. The initial condition that has now 2 values, the set of times, and the list of parameters, okay? In the same order, R, C, E, G, that appears over here. Okay, right? So it's very simple actually to use this. You just have to be careful to be consistent, right? Consistent in the order of parameters, consistent in the order of the returning values of the functions, right? In the initial condition, okay. And then when I call this is simply an array. Let me print this here. So first I'll print the shape of x, and then I'll print x itself. Okay, it's just to see what is going on. Okay, so the shape of x, there's this function. Oh, this enlarge. Okay. Okay, so maybe this was a bad idea. So let me do with less time steps. Okay, then we go back. So yeah, steps of 1. Yeah. So this here is 50 time steps. Okay, and what is the shape of x? It has 50 lines. So each line is a time step, and 2 columns, okay? 2 columns. 1 column, the first column will be the prey, the V, and the second column will be the predator, P, okay? Yeah, and here it is, when I print x, I have this, okay? So it starts with 1 and 3, that were the initial conditions over here, okay? This is exactly the same. And then I have this is with time step of 1, okay? So this I have v at time 1, p at time 1, v at time 2, p at time 2, oops, over here, v at time 3, p at time 3, and so on and so forth until the time 50, okay? And then when I plot this, I get this solution over here. Well, this is kind of boring, right? So what happened here? So maybe let's see if there's any more dynamics. Let me stop the printing here. So oh, it shows the parameters so badly that they went to extinction. Or did I? Ah, I made a mistake over here, right? So this is R times V, right? Yeah? Yeah, so if you write the equations wrong, then you have wrong solutions, right? So, now it is. Oh, now much better, right? So predator-prey oscillations, okay? Yeah? Okay, so now you should have the same in your version also, okay? Questions, people, questions, yes, questions.
It's not really a question, but it's more like an important observation. If you go down a little bit just to show the graphical solution.
Yeah.
So it goes really close to 0.
Yeah.
And if we are trying to describe a biological population, even though it shows oscillations, it would probably just go extinct, right?
Depends, right? So depends on the scale that you're really looking, right? So this is well, this is a complicated question actually, right? So there are things that you can say something like this. Well, if you have very small populations, right, they are more prone to extinction, but also you have to have a lot of trust in your in your model to say that these very low values, population values, are also real, right? So you just say the model is an idealization, and the idealization of the model is such that if you're using continuous values, okay, it means that populations are very large, right? And then even low values, so for instance, what is low here? Is low 0, 1? Is low 1? Is low 0.01? And what are these units, right? So is this density of populations? Of course, if this is absolute number of individuals, you cannot go below 1, okay? It doesn't make sense. But usually you don't do this, right? So you work with densities. And you work with densities. Densities at a large area gives you large number of individuals, even if densities are low, right? So in many contexts, it makes sense to use low values for, even if this goes also 0, even if this is a very small number. So this is one way around this, right? So another thing is, even if, well, there are situations in which this is really important, right? So you could have, in these low valleys, you could have stochastic extinctions, okay? So this, well, there are very few individuals, and they are more prone to extinction due to randomness, okay? This is hard to work with in deterministic models, okay? If you really want to do this and include like Ali effects, I don't know, Roberto should probably have thought about this. So you'd include Ali effects that you say, well, once you reach a certain threshold value, the population doesn't grow anymore, it goes to extinction. Okay, so this is one way to treat this issue in this context. But in general, it's a hard problem. But I think we should be careful about saying something like this. Okay, these predator-prey oscillations are such that the prey reaches very low values. So in practice, you always have extinction after the first value, right? Because this is also trusting a bit too much in the model. You see, because the model doesn't take into account that, well, maybe if prey are very, very rare, it becomes harder and harder for predators to hunt them, right? To find them, okay? And so maybe this valley also doesn't happen. Well, in reality, if you had this density, this means extinction. But does this mean that your model predicts extinction? Or maybe, you see, it's a complicated question, okay? So this is, well, of course, here, this is the computational methods part where we are supposed to be talking about computations, right? So this is really a difficult modeling question, right? I think Roberto talks a lot about this, probably, in his course, I don't know. Well, he hasn't, he probably will when he gets to Lotka-Volterra equations, okay, yes?
In that case, we could also associate with migration instead of extinction. No.
Yeah, you would have local extinction and then you have recolonization, but then this is, yeah, something else, yeah.
You're modeling a closed system, in principle. We expect the solution for these equations. I mean, we have to keep in mind what we're trying to describe here. Lotka-Volterra stands for predator-prey with specialized relations, right? But the point is, yeah, if the population goes to zero, maybe it could be due to migration. But what we're trying to model is an isolated system where the increase in number of individuals is due to reproduction and the loss of individuals is due to predation. So, yeah.
There's a funny comment about this also. And I don't know how many of you have looked at also empirical data, right, on populations, right? But there's something funny about predator-prey systems is that, well, if you look at data, sometimes you have holes in your data, like situations where you almost don't find any prey, right? Or if you look at, for instance, insect collections, there's a bit of an issue sometimes, like, where do they go during winter? And there are species for which this is a hard question. You don't find them at certain times of the year, right? So it's, but they always show up later, right? So it's, even empirically, this is not, looking at very small populations, it's a hard problem, right? So even outside of modeling, okay? So, so it's hard when your system depends strongly on small populations, it's a bit harder to both to model and to understand what's going on, right? So this is perhaps when stochastic models are most useful, right? When you have small changes, random changes will lead to large effects, right? So if you start with a small population, of course, in this situation here, for instance, for the context of predator-prey equations, right? It doesn't matter that much because in the growing phase of when the predator is growing, it grows really almost pretty much exponentially, right? So even if it starts with half of the amount of population, it will quickly reach the same population as before, right? So, so in this situation, it doesn't matter so much, but in other situations, when you have really risk of extinction, it does, right? So I don't have a definite answer for you. I just, it's like here you cannot have a very, you cannot view this in a much, in too narrow fashion, you know? You have to beware of the whole picture that your model paints, right? Even if in the middle there's something weird happening, you have to also look at empirical data and see if this, for instance, one question you can ask is, are populations with large amplitude cycles, for instance, for predator-prey, more prone to extinction? This is an empirical question, right? So you could try to look at that, okay? I don't know, I don't have a definite answer, but then this is a very big question, okay? More questions. So nice question, yeah. More questions? So, okay, so, yeah, we still have some time. So now, what we did here is very nice because now we can solve any system of ordinary differential equations that we will ever encounter in our lives, okay, in our lives, yeah? So now we are prepared, okay, yeah? Okay, so there's one nice thing also that we can do with this that I think Roberto has used it already, is that when you have this X here, okay, X is an array with 500 lines. That is each point is a line, right? Each point in time is a line, and each line has two values, one for V and another for P, okay? And the usual plot is this plotting over time, okay, where you have both populations oscillating, okay? But I also plot what is called the phase space, right? So I plot V in one axis and P in the other axis, okay? And then, and time now kind of disappears, right? Time is changing as I go along the Earth, but it's not explicit in any axis, okay? And when I do this, how I do this, right? So I have just to plot x of 0 here and x1 here, so this is the first column and the second column. When I plot one against the other, right, I have a plot like this. So I drew here this dot here just with the initial condition, right? So at 0, 0 and at 0, 1 with an O here that is a large dot, just to show where was the initial condition. The initial condition was at 1, 3, okay, 1, because this is almost up to 100, okay, so this is 1, 3, okay, so this is the prey values go almost to 100, and the predator values are smaller, right? So go up to 13 here, okay? And what does this do? So in each cycle here, it goes up and down, but you see it's periodic, right? So it keeps, so initially, right? Initially, V is going up, so the prey are going up, and the predator is going down, okay? And then at some point, the prey goes down and the predator goes up, right? So I start here. The predator that is in the y-axis is going down. The prey that is in the x-axis is going up. So I go here, I go up to here, and then I go back. And then I go over here again, and so on and so forth. So I actually, when I plot this, right, I'm going, this goes 1, 2, 3, 4, 5, 6, 7, 8. I go 9 times over this loop here, okay? So this is perfectly periodic. It means that I go over this course here 9 times, okay? Yeah? The fact that the line goes onto itself means that it's working, okay? So lots of equations always give you periodic solutions, okay? And closed circles, yeah? No matter the initial condition, okay? Here, just calculate a different solution with it's actually the same equation, but with slightly different initial condition. So this initial condition here is 10, 4, right? So 10, 4 is 10, 4. It will be here, okay? I think I could put it into the same plot. I think it was best, yeah. So let me put it into the same plot over here, yeah. So this is with 10, 4 as initial condition. And now it gives you another cycle, but it's a smaller cycle, right? So this is one funny thing about Volterra predator-prey equations, is that depending on the initial condition, the cycles are different. They have different amplitudes, different periods, and so on. So this is a bit weird, okay? This is a problem with the equations, not so much with the, yeah? But just to see that it happens in a similar way. I could also plot this over time, right? So let me plot this also over time, yeah. So this is T and X2, right? So T and X2, just to show you, yeah, these are different oscillations, you see? So this is with a different initial condition for predator and prey. Let me also include the legends over here, yeah. Just a moment. So the labels and the legends, yeah, over here. Okay, now it's okay. Yeah. Oh, no. This is T and population. Yeah. Now it's okay, yeah. So you see that for logical Volterra equation, different initial conditions lead to quite different solutions, right? So these are still oscillations, but oscillations with different amplitudes, different periods, and so on, right? Yeah. So I'm not going into details about this because I'm pretty sure Roberto will talk all about predator-prey logical Volterra systems. Okay. Okay, people. So today we have just a bit more time. Yeah. More questions? What are we going to do in the next lessons? Okay. So we're going to try to use this to solve some more equations, right? So I think it's maybe a bit too late to start today, or do you want to start already? So the idea is let's use this library here to solve this equation here, okay? And then we will work a bit on how do we explore this, right? So one thing that I want to go back to is that when I have an important contrast to be done here is that, for instance, let's go back to the logistic equation, right? I could, with the analytic solution, I knew the shape of the solution, the expression of the solution for any value of R, of X0, of K, right? So I already have a complete picture of the solution, okay? When I do numerical simulation, I only have the solution for that value of parameters, for that value of the initial condition, for those times, okay? I don't have the full picture, okay? So if I want to see what happens for other parameters, other initial conditions, and so on, what do I have to do? I have to simulate again with those other parameters, with those other initial conditions, and so on, okay? So you see for logical Volterra here, that is a pretty simple equation. If I change the initial conditions, I change the solution, right? What if I had changed some parameters? What would happen with the solution? So in general, it's a hard problem to understand everything that's going on or that could go on with some equation only with numerical simulation. So with numerical simulation, it's pretty easy to get the solutions, right? To get particular solutions. And the hard problem becomes to get a picture of the behavior for all parameters and initial conditions, okay? That is kind of the opposite. With analytical solutions, it's usually hard to get, or sometimes impossible to get the analytical solutions. But if you have them, you already have a picture, the whole picture, what happens for any values of parameters and initial conditions, right? So the exploration is not necessary, okay? But then a lot of what we will do here is learning techniques to understand the general behavior of differential equations in terms of parameters, in terms of initial conditions, and this kind of stuff, okay? Good, yeah? Okay, so that's it for today then. Yeah, thank you.